Hey, Barney's part of our imagination. And that leads us into our lesson for today. Welcome to the Johnson Kendall Video Hour.
But it's not an hour.
Dang, wish it was. All right, we're going to talk about complex imaginary numbers. Okay, complex means they're going to have an imaginary part to them. Now, if you look up here, we have the square root of -2. Now, if you tried to just do that on your calculator, it would come up with the word error. But
So the answer's error?
oh no. We need numbers for answers, not words. So you have to think about this. If I have a negative times a negative, it's going to be positive. And if I have a positive times a positive, it's going to be positive. So there's no way I can have a negative under the radical because it's got to be the same number twice, either both positive or both negative. So that's why we get the error. Now, mathematicians have decided that the letter I is going to represent our imaginary numbers. And we need imaginary numbers out there in the real world because they're part of quadratics. And we'll talk about that a little later. So the one thing you have to know is that I squared equals -1. That's the big part you have to remember. Or square root both sides and you get -1 equals I.
So I is the only number that if you ever square root a negative, I'm sorry, if you square root a negative, you get the number I.
Correct. Correct.
Okay.
It's kind of a weird concept.
That is weird.
All right, let's try one. All right, so I have a square root of -36. So a little shortcut you got to do here is we're going to take that negative out and it becomes an I. So I like to think of it as it's so excited to come out from underneath the little roof there that it turns into an upside down exclamation point. So we have an I and then just regular square root of 36 is just 6. And then we put numbers first because we're in math class and numbers are more important than letters. All right, let's see if we have another one here. Square root of -12. Well, we don't know the square root of 12, but I can still bring the negative out, so that becomes the I. Square root of 12. Now, we need to break this down. All right, if it's not a perfect square, you must simplify. First, you take care of the negative, which we did by bringing the I out. Now we have to go back and figure out the largest perfect square that's a factor of the number. If I break this into 4 and 3, 4 is the largest perfect square.
What are perfect squares?
Those are numbers that have square roots, exact numbers like 4, 9, 16, 25, all of those. Okay, and then the next thing we're going to do, so we did that and that, we got to split it into two radicals, so I'm going to do that and that, keep my I out front, and then the last thing we do is reduce. So this 4 is a 2, but remember we bring those out front, then you write the I, then the radical comes last.
And the 3 is stuck because it's not a perfect square.
Right. If you're not perfect or imaginary, you can't come out from the little roof.
Oh, that's funny.
All right. Okay, let's try this one. So again, the negative comes out as an I. Square root of 8, I'm going to make square root of 4 and square root of 2 because the 4 is a perfect square. That turns into a 2, so we have 2I root 2.
I like the order you're putting those in.
Thank you. It's important. All right, the next one. We have this 2. The negative comes out as an I. 24, let me think here. 4 and 6? Is there anything bigger than a 4 that's perfect?
12 would work, but it's not perfect.
Right, so we don't want to mess with that. Try to pick the perfect ones. Then you'll get the perfect answer. So 4 and 6. This 4 is a 2. Now I don't see any plus signs, and I can't bring in my own plus sign, so it's not plus. It's all multiplication. So this 2 multiplies with that 2 to make a 4. Put the I, and then the 6 is stuck.
Wow. So now that you know about imaginary numbers, now let's talk about complex numbers. These are numbers that they really have two parts. They have the real part, those are just normal, old, regular numbers that you're used to working with, and if it ever has an I with it, that's the imaginary part. So a complex number is the combination of a real and an imaginary number. I put a little note on the side here for you. For real numbers, like the number 5, technically as a complex number, it does not have an imaginary part. That's why it's just 5. Okay, so we're going to do a few things with these complex numbers. The first thing is graphing them. So we have a plane, and it looks very similar to our normal coordinate plane, but it's actually called the complex number plane. So what you will notice is that what used to be the x-axis is going to be the real axis, so that represents the real numbers, or the a's, and then your y-axis is your imaginary axis, and this is going to represent the imaginary part, or the b's. So the point AB represents the number A plus BI. So I have a couple examples on the side here. I'm just going to move those out of the way. So 5, and then the imaginary part is actually -1. So the real part, or the A part, is 5, and the imaginary part is -1. So graph it just like a normal point. Here's 5, here's -1. There's my dot. 5, -1, which represents a number, the complex number, 5 minus I. All right, next one, -3 minus 2I. So this time the real part is -3, and the imaginary part is -2. So graphing that point, -3, -2, that would be right there. But remember, that's really representing the complex number -3 minus 2I.
A little side note, if you have a graphing calculator, it's going to represent it with the parentheses form. So you have to be able to distinguish between the two.
Ooh, do we do that in trig?
We do.
I was going to say, I don't do that in algebra 2. All right, last one. That's good to know, though. 1 plus 4I. This time the real part is 1. The imaginary part is 4. So that's going to be way up there. 1, 4, which represents the number 1 plus 4I. All right, let's move on to the next topic, and it kind of deals with this complex number plane. What we're going to be doing is finding really the distance from 0 to these complex numbers. And using, to find that, you would use the distance formula. So going from 0, 0, what's the length of the line that would take you to each one of these dots? And if we manipulate the distance formula, we'll actually come up with this. And it's actually the same thing as the absolute value of a complex number. So if you're asked to find the absolute value, what you're going to do is take the A value, which is the number that's the real part, and square it, and the B number, and square it, and then you'll add them together, and then you'll square root both of those.
So you kind of ignore the I
Right.
when you're trying to find absolute value.
Right, and when we do all this squaring, it's going to get rid of all the negative stuff that we have. So let's find the absolute value of 5 minus I. So remember that the A part was 5, and the B part is actually -1 because that's out in front. So we will do the square root of 5 squared plus -1 squared. And using order of operations, what should we do first?
Exponents.
Exponents. That'll be 25, and when you square -1, it'll be 1. Square root of 26. Now, Mrs. Kendro taught you the little trick for splitting things up when they're inside radicals and they're not perfect squares. But I think if you look at 26, the only factors that go into that are 2 and 13. Neither of those are perfect squares, so this is as reduced as it gets. Okay?
Okay.
That is also representing the distance from 0 to that point, which we had here. Okay, the length of that would be the same as the square root of 26. Let's do my other two here. So absolute value of -3 minus 2I. Square root of, take -3 and square it. Take -2 and square it. And then we'll square root the whole thing. Square root of, that'll be a 9 and a 4. That's the square root of 13. Again, I don't think it can be simplified.
Nope, it's prime.
I think that's probably good enough, so let's move on to the next topic.
All right.
Kendro's on.
Woohoo! Okay. When you want to add and subtract, I acts just like a variable, just like your X's and your A's. So in this problem, the parentheses don't really mean anything other than kind of grouping symbols. So when you rewrite this, you can just write it without the negative, without the parentheses, and keeping the other side. So I can put these two together to make 3, these two together to make 13I. And that's it. It's that simple. Don't make it worse
Don't make it worse.
by complicating it, yes.
Complicating complex numbers?
Yeah, it's kind of tough to do. we can imagine it can be done. All right, so this one we have a negative. I need to distribute that first. So I have 8 plus 3i, and then minus 2 minus 4i.
So the parentheses do matter this time.
Right, because it is negative. It's minus.
Got it.
So those two make 6. Those two make negative 1i. Or you can just write negative I.
What about multiplying?
Multiplying x just like regular variables too.
Except
When you're done, if you have an I squared, you must change it to negative 1.
so that means we're allowed to have i's in our answers, but we are not allowed to have I squareds in our answers.
All right.
So pretend for a moment they're x's. If you had 12x and you were multiplying by 7x, you would multiply the 12 and the 7, and then you'd have x times x, which would be?
X squared.
Okay, so we're going to do that only with i's. 12 times 7 is 84. I times I is I squared, but we're not allowed to have that. You must change it to a negative 1. It's the only number in the whole wide world that you square it and it's a negative. And therefore, my final answer will be negative 84.
Well, that's cool.
Let's do some binomials. We're going to have to use our foiling, F-O-I-L, when you multiply two binomials. First times first. So that's 6 times 4. That's just 24. O is outer times outer. 6 times negative 3i is negative 18i. Then we've got I inner times inner. That'll be negative 20i. And then last times last. This is the tricky one. This will be a positive, and it ends up being 15. I times I will be I squared.
Hey, you can't have an I squared.
Can't have an I squared. So we are going to change that to a negative 1, which is going to change that to a negative 15.
Hey, can I put that with the 24?
You sure can. Those are like terms. So we're going to put those together, and we get 9. And then we also have like terms here, minus 38i.
Nice.
And that's it for today. That's our.
Imagine that. We're
Imagine
done.
that, yeah. It's not too complex.
Nah.
This is actually our part 1 lesson. We're going to practice these things in class, and then we'll finish it up.
Sounds perfect.
All right.
Ta-ta for now.